This is an example of a problem where we're going to work out a solution without any numbers, but then you can put numbers in if you want to get a sense of how this feels. So the idea here is that we've got two curved sides, and they make part of a circle. So right here, this orange, okay, they make part of a circle of radius r, and this little red block here is released from rest, so it slides down here, and then it encounters this flat part of length d that has friction. So it's highlighted to let you know there's friction, or though I can draw it sort of like it's rough. So that's where the friction is. And so this is going to slide down, go across the curve, and then slide back up if it makes it there, and then slide down, slowing down as it goes across that center section. Maybe not go up as high, maybe go back and forth. Depends on the values here as to how far it's going to go back and forth and how long it's going to last. And so we want an expression for that. So we can sort of start by saying, hey, let's look at this point. That's our initial point A. Let's say what's going on at point A. So we've got gravitational potential energy. I'm going to call this my y is equal to 0. So that would be my gravitational potential energy is equal to 0. So at point A, I have gravitational potential energy, UA. I don't have any kinetic energy, and I don't have any energy that's gone into thermal yet. Okay, then I could look at point B, and if I look at point B, well, now all of that energy has gone into kinetic. I have no potential energy, no gravitational potential energy, and I still haven't lost any to thermal. And let's say we go all the way, so that's point B. Let's go to C. Let's say it gets all the way to C. Then there's C, where we've lost some kinetic energy, and we've gained that same amount in thermal, right, due to friction. So this is kinetic, and in this case, the thermal energy would be the same as the absolute value of the work done by friction, which would be mu times the friction force times the distance that we went. Okay, great. How do we know how many times? And then, of course, it's going to go up some distance, maybe to D. It's not going to go all the way to the top. Well, we can keep doing this for as long as it goes, but we know something about the final. And this is really the trick. In the final situation, it's not going to stop on these upper walls because they're perfectly slick. So it doesn't have any way to stop. So it's going to stop somewhere down here. So our potential energy is going to be 0. Our kinetic energy is also going to be 0. So all of our energy that we had at A, right, this is going to be the same, is all going to be thermal. And it's going to be given by that. Well, not quite. The total amount is going to be mu. It's going to be mu times, sorry, not force of friction, that's force normal once I've multiplied the in there, sorry, force normal, so mu, and on the flat part, force normal is just mg, mu, mg times the total distance, however far it travels. If it goes back and forth 3 times, 4.7 times, whatever, the distance that it travels. And so really, all we have to do, we can skip all these in-between places and say the energy here must be equal to this. And that seems fairly straightforward to do, so I can say mg times the height, that's this right here, height, is equal to, well, mu mg times the total distance that we travel of the flat. Distance on the flat, on the horizontal surface. And this height is just the radius of the circle, right? This is a distance r, so that means this is a distance r. So this is mgr is equal to mu mg, distance on flat, So the masses cancel, g's cancel, goodness, and it's just r over mu gives us the distance it goes on flat, which you could write if you wanted as some number times this distance d, and so that n is now the number of times it goes back and forth across the flat. So if it goes 2.5 times, that would be 2.5. So you really just need these two numbers for this particular setup, and you can get at everything else that you need, which is really nice. It's a lot less complicated than it looked like when we were starting this problem.